Okay, so hello to all. It was an amazing 2 months camp. We are finally here to conclude the advanced camp as well. So I would just summarize the camp, and we have a special guest today. We have Venkat sir from 0x PPL. We would have a talk with him later. So we'll summarize the camp. We had around 12,000 plus students reach, 70 plus institutions across the country, 25 lectures, and three contests. We will be having the last contest around 20th of August. We are still preparing the problems. We had two amazing sponsors, 0xPPL and Algogenith. We had 20 plus lectures. I think all you can find on the our website. So this will be the last advanced camp session taken by Aryan Agrawal. He would be taking the lecture on Moose algorithm and range queries. And as we had promised, the attendance to all the lectures will be given if you attend this final lecture. So it's as a souvenir from our side. So we have two sponsors. First is Algogenith and other is 0xPPL. We especially thanks to our both sponsors without whom this camp would not be a success. We hope that this camp was at par with the expectations of our sponsors and look forward to work with them in future. We are planning for a few more steps in the future. We'll share the details. And if you can get involved or sponsor us to boost our next endeavor, you can reach us to at iscpc.india at the rate gmail.com. We have a website iscpc.com. So Vivek Gupta sir was not able to join us due to some lectures here right now. There is Algogenith. Algogenith stands as one of the India's premium platform for internship and placement preparation. Right now, the intern season is going on. Their programs cover DSA development and competitive programming and extend to resume building, referrals, and several other stuffs. Their track record of having many students from even tier 3 colleges reaching Google and other big companies is really impressive. And we thank Vivek Gupta sir for finding time in taking our DP lecture and also Algogens to sponsor us. That lecture was very nice. It was the first lecture of advanced camp, and it was really an amazing lecture. We have second sponsor 0xPPL led by Prasanna Sankar, and today Venkat sir will be representing 0xPPL here. 0xPPL is an emerging Web3 and crypto firm for the young generation led by Prasanna Sankar, who was earlier the founder of Rippling, which is currently over $10 billion company. He was also the rank one in several coding competitions like Google Code Jam, Top Coder, ACM, ICPC at the age of 18. 0xPPL has inspired several ICPC world finalists. And thus, if you are passionate about competitive programming or programming in general, you can connect to him if interested in internship or placement opportunities at prasna at 0xppl.com. So we had taken 50 students from the first contest, 50 students from the second contest. We'll just make another, most probably, Code Forces group to have the final 100 students. We'll be having the final ICPC contest around August 20. We'll finalize the date and inform to you all. So, what exactly next after this camp is over? That is a question a lot of people were asking. And so we are here on YouTube, Discord, and WhatsApp communities. So you can always be a part of IICPC community consisting of a lot of IITians, lot of competitive peer groups in programming. We'll come back again with a much diverse and better camp from our side and help Indian institutions grow in programming. Obviously, this was the prime goal. We had this camp for over 2 months. We wanted the programming to spread throughout in the country, especially in the institutions where it's not having too much grip or something. You can support us with whatever help you can by the YouTube thanks and membership so that we can continue delivering the best to the communities. Right. Apart from this, let's thank all of our lecturers. Despite their busy schedule, they helped a lot. They had interns and several other stuff. Still, they came forward to help us in this camp. You can find all the lecturers in our website, iscpc.com. So there is one more thing. We are launching ICPC merchandise. So you can buy it. If you buy, there will be a kit consisting of 3D logo. You can become a part of our community. It will be a totally non-benefit moment. Like it won't benefit us a single penny. Let's make this merge to be a part of our diverse community. We'll be having a separate community for these people as well, who would be showing respect and dedication to us. Merge will be delivered to your location, and link will be given in the Discord and WhatsApp communities. So thanks to you all for attending this amazing camp. I never expected 10 to 12,000 people joining us in the camp. So it was an amazing journey, 2 months journey. So we are here with the three organizers. I'm Ayush from IIT Madras with my friends Aitya Misra from IIT Delhi and Gauris Balika from KJSC Mumbai. So now we invite Venkat sir from 0xPPL. We can have a talk about 0xPPL. And so, hello sir, are you? Uh, can you
Yeah,
hear me? Okay,
yeah,
sure. So,
cool.
can you explain your journey first of all? Like you
Mm.
left Google, you were. So let me tell about Venkat. Sir. He was 2 times ICPC World Finalist. Am I right? Right. Okay. And then he was IIT Bombay graduate. Then he went to Google. Then he left and joined to 0xPPL as a founding engineer with Prasanna Sankar. Sir. So, can you explain this journey? How you did this
Yeah,
transition from Google to 0xPPL?
yeah. I mean, as you said, like in college, I was very much into competitive programming. Like I used to do a lot of coding. Been to ICPC World Finals twice in 2016 and 17. In 17, like we were the best performing team, like we in India. So yeah, after that, yeah, I worked in big tech for about like 4 5 years, and then realized like I want to like bet on myself and like take work in a startup at a very high paced environment. So that is when like Prasanna contacted me regarding this opportunity, which I felt was very fascinating, especially because like I felt like it is a time where like something of the order of magnitude of internet is being done. Like I was
Right.
not around when internet was being like um, built, like how web 2 world was built. Like I was very small then, I didn't know what what is happening and all of that, right? So but when I got in touch with Prasanna and learned about the vision, I felt like this is something of that magnitude that is happening, that is with crypto basically. So yeah, so wanted to be on the frontier, like build, yeah, like we build like pretty deep tech uh, that will like solve or
Right.
not
So,
solve, like basically get to the
can you
vision of,
explain about what's the 0xPPL exactly do like in the crypto
yeah.
form? I mean, we just know from the surface knowledge what Web3 and crypto is. So, if you could
Yeah,
explain it better, we will be able to understand it.
sure. So yeah, at Xerox people, we are trying to build a decentralized social network where people will be able to follow blockchain addresses of their friends or the people that they know, and then they'll be able to see the transactions that they're doing, because blockchain is permissionless open backend, right? So basically like anything that is done on chain or like on blockchain is public, right? It's just
Right.
that like everything is so cryptic, like all of them are addresses and like hexes and stuff. So we're trying to make it very manual, like easy for a human to read and understand what is happening on blockchain. I mean, that is what we think where the future is. Like, eventually, people wouldn't be using like hexes and stuff. People will be using names. Like, this address belongs to this person. Like, that is much more valuable than saying this address has this much net worth, right? So, yeah, we do a lot of very deep engineering work. Like, we have like the best engineers in India, like multiple ICPC World finalists, like ranked one in India. Yeah, like we have a pretty great tech team. So, and yeah, I lead like all of the engineering efforts at Zero X People. So yeah, that's briefly about Zero X People.
Right. And this is totally unplanned. I mean, the discussions are so it's mostly like casual talk, okay, because you are also like a student with this. So,
Yeah.
few more things like many of people were interested in most interns opportunities or as in. So, what? How can they connect or something? Can you explain us?
Yeah. So yeah. So we are open like to hiring great people. Like basically, we have a great vision. Like we're chasing after like anybody we feel like can fasten up that process to get to that vision. Like we're always hiring. So yeah. like to be clear, like we are not trying to hire like short term interns, like some like at least like 6 months kind of interns. We're trying to hire like, because 2 months is a too less of a time to nurture an intern and like actually the intern themselves providing value to the company. So yeah, we are looking anywhere greater than 6 months. So yeah, I mean, like as I said, like we have one of the best engineering teams, like uh, um, like multiple ICPC world finalists and XYC founders. Like so, yeah, we have a pretty strong team. So anybody like who is wanting to grow like exponentially, like right out of the college, want to just jump into the deep tech engineering, and yeah, also just develop an entrepreneurship mindset. Happy to um, like interview them. Like yeah, you can just contact me over LinkedIn or like or my mail. So yeah.
All right, sir. And how about the camp? Did you go through the camp, like how it went, and so would you
Yeah.
comment something on it? Like how are we doing?
Yeah. So while I'm building Rex, people, yeah, wasn't really didn't have the bandwidth to go through what's happening in the camp. But yeah, I mean, these are great opportunities. Like, I mean, when I was doing coding, like there are venues like this where people across IITs can coordinate. Like, there's a competitive programming club. Like,
Right, exactly. Even competitive programming is not there in inter IIT also right now. Also. I think it was not there in your time also, if I recall
yeah,
correctly.
yeah, it wasn't.
Right. So we can make it happen like in the inter IIT as well, this competitive
Hmm.
programming. Maybe we can
Yeah,
try. I mean, this was for all the institutions in the India, and basically that's the goal. So it's not restricted to IITs. So it's better, and we can
yeah,
it's far-fetched goal. I think. Okay. So we can continue with the session. I think.
yeah, yeah,
Okay.
sure.
Thank you very much, sir, for joining us.
Cool. Thanks a lot. Yeah, please feel free to contact me. Anybody who's interested in the opportunities. Venkat at the rate of zeroxpeople.com is my email. So, or you can contact me on LinkedIn. Cool. Awesome.
Okay.
Thanks a lot, Ayush.
Okay. Thank you, sir.
Yeah. Bye.
Bye. Okay, so we can start the session today. We have Aryan Agarwal from IIT Roorkee. He will be taking Moz algorithm. So Aryan, you are here.
Yeah, hi Ayush.
Okay, can you screen share?
Yeah, Ayush. Is my screen visible? Hello?
Yes, it's visible right now.
Yeah, cool. So, hello everyone. I'm Aryan Agrawal from IIT Roorkee, a final year student, and now I'll be taking this session on square root techniques. So, square root techniques is a set of techniques which are used for solving several types of problems in competitive programming. And these these techniques are called so because they use some sort of square root heuristics, like they may be uh, dividing the queries into batches of square root, or they may be dividing the data structure into batches of square root. uh, any kind of heuristics can be involved in these techniques. So most is one particular special category of these techniques, and yeah, several range query problems can be solved using most, but we'll start from the most basic one, which is square root decomposition, just square root decomposition. So in this particular technique, what we do, we divide. Okay. So we take an array. Let's say we have been given an array. We divide the elements into batches of square root n size. Let's say the size is n. So root n, almost root n. root n or almost root n, both are fine. So uh, starting with the most basic operation, let's say you have to add some elements from Li to Ri. So what you can do, you have already divided uh, these elements into batches of size root n. So you can process, let's say this is a batch, this is a batch, this is a batch, this is a batch. So you can, let's say if the Li is here and Ri is here. So for those batches which are completely uh, inside the range of the query, they can be pre-computed earlier. For example, you have already pre-computed the sum of this particular batch. Sum of this particular batch is also there. Sum of this batch is also there. So the sums of the batches are already there. So you can take those sums as whole, and for the elements which are not whose batch is not completely inside the range, you can add these separately. Okay. So if there are n elements in total, dividing into batches of size square root n, you have square root of n batches into batches at max. So for every query, you will have to uh, take root n batches at max plus some elements here, will also be will also be the order of root n only. So overall root n multiplied by q, because q queries will be there. So q root n is the complexity of the problem. So you will ask, we can solve this using simple prefix sum or segment trees if you want to, but and both of them are quite faster compared to the square root technique or the square root algorithm. So there are several problems which cannot be solved using prefix sums or segment trees or sparse tables. So in those problems, we'll use these techniques, square root techniques. I can show you an example. So this particular problem I have here. Okay. So this is a problem from code courses. It is named as Sergal and Fun. And in this particular problem, you have been asked. Okay, yeah, I'll read the problem statement itself. So you have been given an array A consisting of n positive integers and queries to it. The queries can be of two types. Make a unit cyclic shift to the right on the segment from L to R. That is, if the range initially is AL plus 1 dot dot AR minus 1 AR, then it will be changed to AL dot dot AR minus 1. So you have to shift it by 1 unit to the right, and then you have to calculate the numbers which are equal to k on a given particular segment. If you look at the queries, let's say this is the initial array, and these are the queries given to you. So in the first query, you are asked to cyclic shift the sub-array from 3 to 6, and then in the second query, you are asked to calculate the number of 2's from 2 to 4. Okay, so let's dive into this test case. So the first query is to cyclic shift by 1 unit the subarray from 3 to 6. So this is the third index, this is the sixth index. So we shift this cyclically by 1 unit, and we get 6, 6, 2, 2, 7, 4, 5. Okay, so after cyclically shifting by 1 unit, it has asked us to compute the number of 2's from 2 to 4. So from second index to fourth index, the number of 2's are 2 only. So the answer for the first query will be 2. First query as in first answer query. So this will be 2. As you can see in the output, the answer to the first answer query is 2. So these are the queries which we have to handle. Okay. So what we can do here, let's say you have the brute force solution would be to like let's say you maintain a vector or a doubly-ended cube for the whole array, and then you remove these elements, and these elements, if the query is from here to here, shift query is from here to here, then you shift this array by 1 unit. After that, you add these elements in the front and these elements at the back, and this complexity would be O of n for a single query. And for Q queries, the overall, okay, one query, it would be this. For Q queries, it would be O of nq, which obviously is not up to the mark. As you can see, there are order of 10 raised to 5 queries and order of 10 raised to 5 is, elements. So what we can do here, we can divide the complete array which has been given to us. Say A1, A2, AN is the array which has been given to us. We can divide it into batches of 10. And we can create a separate frequency array for each batch. As the numbers are only from 1 to n, so the size of each frequency array would be n, and there are root n frequency arrays in total, so the total size of the frequency arrays would be n root n only. Okay, so like you can create a frequency array of size n root n or a 2D array of size n root n. So we will maintain the frequency individually of these batches, and what we'll do, we'll also create a doubly ended queue separately for each batch. Let's say you have a doubly ended queue for this batch, a doubly ended queue for this batch, a doubly ended queue for this batch, and for this batch as well. Now, if you are asked to perform a query from here to here, so what you can do, you can just for this particular, sorry, yeah, for this particular batch, you have to shift the uh, this element will move here, this element will move here, and the first element from this batch would become the last element from the second batch, and this element would move here. So from the first element from this batch would become the last element of this batch, and here we have to cyclically shift this. Okay, this will go here, this will go here, and this particular element, it will become the last element of the range. Okay, so for the batches of size square root of n, you can just remove this element from front, add this element to back. For this range as well, you can remove this element and add this element to back. For the remaining elements which are here and here, you have to like remove these elements out, and then after modifying, you have to put these elements back. So if the elements here are 1, 3, 5, and the element here is 7, so you'll have to take 1, 3, and 5 out, and then you'll have to put 3 and 5 back with 7, and 1 will move to this place. So 1, 3, 5, 7 will become 3, 5, 7, and 1 will become the last element of the range. So using this W800Q, you can perform these operations. So if we try to analyze the complexity of this particular operation, it will be uh, okay. So for each batch, we are performing an order of one operation. We are removing this element, and we are adding a new element. So order of one operations are being done for a separate batch, and for these elements we are performing order of root n operations. So root n operations for the batch, the first batch, root n operations for the last batch, and O of one operations for all those batches, all those batches which are in between. So order of one for root n batches at max, and order of root n for two batches. So ultimately it would become order of root n for each query. And you have uh, Q queries, so overall the complexity will become order of Q root n. So this is for the queries only. For updates, sorry, this is for the updates only. For queries, uh, you can just sum up the frequencies. Let's say if you want to query for the number x, then you can just sum up the frequencies, frequency x from this batch, frequency x from this batch, and you can count the number of instances from number of instances of x from here, and you can also count the number of instances of x from here. So it would again be order of 210 only, because like root n batches are there, and you are performing order of one operations on every batch. And for the first batch and the last batch, you are performing order of root n operations. So you have to check the elements one by one, all these elements. So this is how you can answer the queries as well. I can show you the code. Yeah. So I have assumed the square root number to be 340 actually. So I have created 340 batches, and frequency array of all those 340 batches are there. And I have created a W100 queue for each batch. 340 W100 queues are there. 340 is an approximate number I have taken. Uh, you can calculate the square root and take that number as well. But yeah, uh, like square root of 105 would be around 340 only. So I've taken this number. And yeah, first I am pushing all the elements into the W100 queues, and I'm also updating the count, which is the frequency array of all the batches. And yeah, whenever there is a query, whenever there is an update query, I am okay. Just a second. Yeah, whenever there is an update query, I am taking these elements and copying them from the W100 queues. These 100, these elements I am copying, and these elements I am pushing here. So, as I said, this element is being popped out. This element is being pushed in, and the element is becoming the last element of the range. You can do it of your own. It's not that tough. The coding part, the implementation part is there, which is uh, not very tough in my opinion. And yeah, this is one of those problems where you can't use segment trees or prefixum or anything. You have to build square root batches and process the problems, process the queries. Okay. So coming to the second part, which is the Mohs algorithm. Mohs algorithm is a special case of square root decomposition only. I'll show you how. So let's say you have been given an array, and in Mohs algorithm we we process the queries in an offline manner. So we have been given these queries. That's it. These all are the range queries which you have to process, and you will sort these ranges in a particular fashion so that you can handle the queries in an offline manner. So let's see how it is done. First, we divide these queries. Let's say LI, L1, R1 is the first query, L2, R2 is the second query, Ln, Rn is the LQ, RQ is the qth query. So after dividing these into segments of root size, what we'll do, we'll sort these queries on the basis of LIs. The LIs of like all those LIs which are from the first segment will be placed first. Uh, let's say this is S1, segment 1, segment 2, segment 3. So all the LIs from the segment 1 will be placed first. All the LIs of the segment 2 will be placed second, and so on. And the RIs of these queries would be sorted in a decreasing order. So our first priority is to sort the queries in the order of their segments. After that, we'll sort the RIs according in the decreasing order. So I'll show you an example. This is the array. This is the first segment. This is the second segment. This is the third segment. Approximately root m is the size here. So this is the first query. This is the second query. This is the third query. This is the fourth query. This is the fifth query. This is the sixth query. 1, 2, 3, 4, 5, and 6. Okay, so for the sorting of the queries, we first take the queries whose li lies in the first segment. So which all qualify for this? 1, 2, and 3 qualify for this. So we'll take first 3 queries and we'll sort them in the decreasing order of their RI. So the maximum RI is with query 1. So query 1 will be there, like Q1 or L1 R1. Then the second query would be query 3 because the RI of query 3 is greater than the RI of query 2. So L2 R2, sorry, L3 R3. The third query would be query 2 because it is the last one whose LI lies in the first segment. So L2 R2 would be the last query in the first segment. And after that, we'll take the second segment. So this is the query. So as the RI of sixth query is greater than the RI of fourth query, the sixth query comes first, L6 R6. Then the fourth query, L5 L4 R4. After that, we'll move to the third segment, and the only query there is L5 R4. So in this manner, we have sorted the queries. So we'll first apply brute force solution for the first query. We will iterate through all these elements one by one, and then we'll compute the query which we have to. So for now, let's consider distinct value queries only. So you have been asked to answer how many distinct values are there in a range from Li to Ri. So we'll iterate from A2 to A6, and we'll calculate the number. We'll count the number of distinct values which are there, and then we'll print the answer. So now we have to modify our range. Like if the Ri is here, we have to leave the elements from last and If the li is here, we have to include the elements from first. So you have to shift the ri and the li according to the next query. And if you have to include an element, you increase the frequency. If you have to exclude an element, you decrease the frequency. So for distinct queries, let's say the existing range is here, the new range should be here for the next query. So you leave this element, you leave this element, you leave this element. You decrease the frequency of this element by one, you decrease the frequency of this element by one, you decrease the frequency of this element by one. And then you take this element, take this element, take this element. And you similarly increase their frequencies. So let's say this is the frequency table F0, Fn, and these numbers are 2, 3, 4, 8, 2, 4, and 1, 2, 5. These are the numbers. So initially the answer is 5, as there are 5 distinct values here from 1 to 5. So F0, F1 is 1, F2 is 2, F3 is 1, F4 is 1, and F5 is 1. Now, first let's say you shift the left pointer. So the left pointer goes from the first index to the third index. So you leave 2 here and you leave 3. So as you leave 2, the frequency, this frequency would become 1. Then as you leave 3, this frequency would become 0. Now note that whenever the frequency goes from 1 to 0, the element is no longer existing in the range. So you have to decrease the counter variable by 1. So the counter was 5 initially because 5 distinct elements were there. And as the frequency goes from 1 to 0, frequency of 3, the counter becomes 4. Okay. And after that, we try to move the right pointer, which is here initially, which is at the fifth position, sixth position. And so, yeah, the pointer is here at the sixth position initially. So we move it to 7, 8, and 9th position. So while moving, when we first encounter 8, we make f8 equal to 1, which was 0 initially. So we make it 1. And you can see here as well, when we are increasing the frequency from 0 to 1, we are encountering a brand new element. So like the count of distinct elements is going up by 1. So you need to increase the distinct count, which was initially decreased from. So after excluding 3, the counter had become 4. And now when we encounter 8, the counter has become 5 again, because 8 is a new distinct element. After that, we encounter 2 again. So the counter of 2 would become 2. And then we encounter 4. So the counter of 4 would become 2. And in both these in both these increments of the frequency, we are not encountering any new element. Let's say 9 is also there, and the range is till 9. So if you want to include 9 as well, then frequency of 9 would also become 1. And also, as you are encountering a new element, you will increase the answer variable to 6 by 1 unit. So this is the way the Moore's algorithm works. I'll show you the time complexity, how it is obtaining O of n root n. Okay. So these are root n batches, keys of size root n. Okay. And okay, yeah. So So you are processing those queries first, whose li comes in this particular batch. Then you are processing those queries whose li comes in this second batch. So while processing a particular batch of LIs, the RI is sorted in decreasing order. I mean, so the RIs are sorted in decreasing order. So first this, then this, then this, then this, then this. So what happens here is that the right pointer moves by order of n only. It will only move from the last element to the first element once. And the left pointer, let's consider the right pointer only. So for every batch, the right pointer is moving once only from the last element to first element. And as there are root n elements, the movement of right pointer goes to order of n root n, order of n times for each batch. And and each operation we saw here was of one only, increasing this frequency table and increasing or decreasing the count of the distinct elements. So, and now coming towards the moving of left pointer. So the left pointer is moving at max root n number of times in a particular batch. And let's take the worst case. So you are here at first, the left pointer is here at first, then it is moving to here, then again it is returning back to here, then again moving to last. So at max over floating times the left pointer has to move while processing the while processing one query of one batch. And overall this goes to the last batch, but like that is O of n overall. So once it has moved from the first batch to the second batch, it is never returning back. So overall, moving from first batch to the last batch, it is order of n. And for addressing the queries, it moves from the first element the first element of the uh, batch to the last element of the same batch. So it is order of root n only. O of n is only once. And into one, and order of root n for q queries which are there. So the final complexity comes out of the query. The final complexity of the query comes out to be order of q root n plus n root n overall. So let me show you a problem. This is quite a simple problem. So here the number n as well as the number t. T is the number of queries here. So the number n and the number t, both of them are the order of 2e5. Okay. So so the overall complexity becomes, you can also consider q to be n because both are of the same order. So this ultimately becomes O of n root n. Q equals to n in most cases. Okay, I'll explain this question now. So you have been given an array a1, a2, an, and let us consider its arbitrary subarray al to ar, where l is from 1 to n and r is greater than l and from 1 to n only. So for every range, you have to calculate ks into s. Let me simplify the question here. So you have been given an array and this is the range, let's say from Li Ri, you have to find the sum fs square into s for every s which lies in the element. For the elements which don't lie in the range, the frequency would be zero only. So let's say this is for all values. Okay, not R. This is for all Z. Yeah. So how you proceed? We use the Mohs algorithm and we divide these into segments and we order the queries as I told you earlier, and we'll process these queries in the batches only. Let's say you are considering this particular range now. So this range you have already taken. So you have the frequency table already set. F1 is the frequency of 1, F2 is the frequency of 2, F3 is the frequency of 3. Now, whenever you encounter a new element, uh, let's say you are encountering 2 and the frequency of 2 is F2 initially, and after that it is becoming F2 plus 1. So F2 to F2 plus 1. So in your answer, what initially was the value which was contributing by which was being contributed by 2? It was F2 square into 2. Okay, and after that F2 is becoming F2 plus 1. So the new sum would be F2 plus 1 square into 2, which is equal to the previous sum plus previous sum plus F2 plus 1. Okay, this is the new sum. So whenever you are increasing a frequency array, you can just add 2 times the new frequency or 2 times the old frequency plus 1 into the number. So if the frequency of I is becoming fi plus 1, you just have to add I into 2fi plus 1 into the answer. And if fi plus 1 and fi is becoming fi minus 1, then you have to subtract minus I to fi plus 1. Okay. Let's include what would be in this case. I square into I minus. So this comes out to be 2fi minus 2. So this is the crux of this problem. You can try coding this problem of your own. It is the first and the most basic, most algorithm problem you can find on the internet on code forces. So you can try coding this yourself. Moving to the next questions or the next technique. So the third technique over here is batch processing of queries and reconstructing the structure. So what exactly is meant by batch processing of queries and reconstructing the structure? Let's say you have a data structure of order of n. Let's say you have a tree or anything which is order of n only, and you have been given few queries to process on that particular data structure. So what you can do, you can divide the queries Q1, Q2, Q1. Let's say n queries you have been given. You can divide the queries into segments of size root n. Or if there are q queries, then it would become root q. And you can process these batches as a whole. Like you can first process these queries, then you can process these queries, and then you can process these queries. And after the processing of each particular batch, what we can do, we can reconstruct the complete data structure. For example, you have processed these queries first, okay, and after processing, you create the data structure from scratch. So you are creating the data structure a total of n root q, sorry, a total of root q times. So overall, if the construction of the data structure is order of n, the ultimate the ultimate total complexity which goes to the creation of data structures is order of n root q. So n root q for one construction and root q constructions. This is one construction, this is one construction, this is one construction. After processing of each batch of root q queries. So overall construction complexity would become order of n root q. Okay. And while processing a particular query, as you have q queries, so the maximum complexity which you can contribute to answering of a single query would be order of root n. And yeah, so let's say you have this the data from all these queries available. You have to answer this particular query. So you can iterate through these data and you can take the info from there and you can answer the query. You have the data structure created, you have these data, and you can answer the query. So query answering complexity would be order of root q for one query, and for q queries it would become order of q root q. So the overall complexity of answering these queries, and if the data structure is of order of n, the overall complexity would become order of n root q plus q root q. I'll show you using the question. You will have a better understanding when I show you an example. And so this is the example I have taken. Okay, so this again is a problem on code faces. This is named Xenia entry. Okay, so what this question requires us to do is that we have a tree consisting of n nodes initially, and these nodes are indexed from 1 to n. We will consider the nodes to be initially painted red and the other nodes to be painted blue. First node is red initially and the rest nodes are blue. So this is the tree which has been given to us, and this node is red, the rest nodes are blue. We have to perform two types of queries on this tree. For the first query, we have to paint a specific blue node in red. So if the first query is performed on this node, then this blue will become red. And for the query of the second type, we have to calculate which red node is closest to the given one and print the shortest distance to the closest red node. Okay. So if the blue, if the second query is on the type on the node, uh, I'll number these nodes: one, two, three, four, 6. So if the second type of query is on this particular node, then the closest red node would be the node 3. And similarly, for any query of type 2, you have to find the closest red node and you have to return the distance to the closest red node. Okay, so first let me go through a brute force solution. What you can do, you can maintain a list of red nodes, and you have maintained a vector of red nodes which is initially only one, and after that whenever you are coming across a new red node, you are pushing it into the vector. Let's say in this case 3 has been pushed, and for answering the distance from a blue node to any of the red nodes, you can iterate through the list of the red nodes, and you can find the minimum distance and you can return that particular red node. But this obviously is not optimal, as the number of red nodes would ultimately become n maximum, and there are few queries. So for each query, you will have to run through n different nodes. Also, the complexity of computing the distance between two nodes is order of log n. So the overall complexity of brute force complexity will be order of q log n. Order of n log n for processing each node, each red node, and q queries in total. So order of n to log n is not allowed generally, and we have to obviously better it. As you can see, the n is 25 and also is 25. So how we can better it? We'll divide the queries, as I said, into batches. So updates only we'll divide. So you have n updates in total, because in a particular update you are turning the blue node red, and there are n blue nodes in total. So ultimately the blue nodes will become red nodes, n in total. So we'll divide uh, we'll divide the queries into size of root n. So first root n updates, then again root n updates, and after each batch of root n updates, we'll construct a fresh tree, or we'll DFS traverse on the tree. So then again root n updates, then fresh tree or DFS traversal on the tree. So while doing a DFS traversal, what we can do, we'll traverse from all the red nodes and update the distance to all the red nodes. Let's say this is the tree we have currently. Mm, This is the red node, this is the red node, blue node. blue node, blue node, blue node. So we'll traverse from all the red nodes and we'll update the minimum distance to a red node for every blue node. We'll start the traversing from here and then we'll start traversing from here and we'll maintain uh, answer array for we'll maintain an answer array for all the blue nodes and we'll update answer of I equal to minimum of answer of I distance or level of DFS traversal from the particular node level. And whenever we come across a visited node, we stop there because we want our we want the overall DFS traversal to be order of n. So we stop whenever we come across a visited node. We maintain that node obviously, and yeah. And after that, while processing the queries, what we do, let's say if we have to process the query here, and we have already done these updates, and we have not created a new fresh tree considering these updates. So we will maintain the red, we'll maintain the vector of the red updates which are already done. So R1, R2, Rn are the red nodes now, which are already there. So wait, my screen sharing this. So, just a second. Guys. Yeah, the screen should be visible now. So after the construction of, after every root and updates, we construct the fresh tree, but we have not received root and updates. We have received some RN updates till now. Sorry, R2 updates till now. So we are storing all the updates in a separate vector, and after creating a new or fresh tree or freshly DFS traversing the new tree, then we clear the updates vector. So right now we are having these updates with us, which we have not incorporated into our tree. So we'll iterate through this list of updates, what we were doing earlier in the brute force, and we'll calculate the distance to each of these red nodes, and we'll take the minimum. So if if after DFS traversing the answer of I is answer I, then we'll uh, for every I in R, we'll update answer of Ri in R. We'll update answer of I equals to minimum of answer of I and distance between I and Ri. So this particular distance can be computed in order of log of n. So the overall complexity becomes order of. Okay, let's handle queries and updates separately. So for updates, order of n root n for creating the fresh tree root n times, and for queries, order of q root q log n. Log n for addressing uh, q root q log n for addressing a single query, and there are q queries in total. So q root q log n. How is this root q coming here? There are root q updates in total which have not been incorporated in the fresh tree, and we'll address them one by one. And the tree which already has been created has the answer of like all the updates which were done before the creating of the fresh batch. Mm. I mean to say that if you are updating this particular query here, so you will consider all these updates one by one, and these updates are already there in the fresh tree which has been created here. So the overall complexity becomes root q, which comes from here, root q log n for a single query, and q queries are in total. So query handling complexity becomes order of q root q log n. Okay, and yeah, the first problem which we did, which was Sargent tree, sorry, Sargent one. This can also be solved using this particular batch processing approach. So you should also try that. Now moving to the fourth category of square root technique. This particular technique, in this particular technique, we classify the objects or the elements into heavy and light, and we take different approaches for dealing with heavy objects as well as the light objects. I'll show you an example. Let's move straight into the problem now. The problem is a simple one. Yeah. Okay, first let's consider a basic example. So you have been given a graph, and these are the edges on the graph. So overall, m nodes and m edges are there. So how many nodes will be there which have greater than order of root m edges? So the number would be order of root m only. So root m nodes with greater than equal to root m edges, because the total edges are in m. So what we'll do, we'll handle these two. We'll handle these two category of nodes separately. One category would be the nodes having less than root m edges, and the other category would be the nodes having greater than root m edges. So these all these nodes come into the second category, which I am referring to as heavy, as they have greater than root m edges, and the other category would be the remaining nodes n minus beta. First category, which is the category of light nodes. So we take different approaches from these two for these two categories of nodes, and we try to tackle the problem. This is a heuristic approach only, so let's see how it goes. So in this particular problem, you are given an array A1, A2, An and m sets S1, S2, Sn of indices of elements of this array. So there are m sets, and in S1 you have, let's say, 2, 3, A2, A3, A7. In S2 you have A2, A1, A6. The elements of the array are A1, A2, A1. So there are m sets, and all these sets have some elements there. So these are the elements of Sn. So what we have to do, what the question is asking us, we have to perform two types of queries. The first type of query is that we have to find the sum of elements with indices from set Sk. Okay. So we have to perform. Let's say we have been asked to perform the first query on S2. Then we'll perform A2 plus A1 plus A6. Okay, if there are only three elements, we have to perform A1 plus A2 plus A6. For the query of type 1 on second set. So this for the format of this query is question mark A. So if the query is question mark 2, then we have to perform this summation. And the second type of query is to add number x to all elements at indices from set Sk. So if we have to perform the second type of query, we do, let's say we have to perform the second type of query on S1, and these are the elements. So we do A2 plus equal to x, A3 plus equal to x, A7 plus equal to x, because all these three elements are present in S1. So this is the query, and this is the update. These are the two types of queries which we have to handle. Okay. So what we'll do, so you can see this particular line here. It is guaranteed that the sum of sizes of all sets Sk doesn't exceed 25. What does it mean? So let's say A8 is also there. So the size of S1 equals to 4. The size of S2 is equal to 3. The size of Sn will be some, let's say 2. If it increases. So the sum of the sizes of all the sets, summation of sizes of Si, I equals to 1 to m sets are there, will be less than equal to 1.5. Okay. 1.5. Now, one key observation would be that how many, if I consider this element to be n, this number to be n, so how many sets would be there in which the number of elements is greater than the order of root n, greater than equal to root n. Number of sets with greater than equal to root n elements. Okay. It would be root n only at max. Or it would be less than equal to root n. Okay. So, as I said earlier, we can adopt two different approaches for heavy sets greater than equal to root n elements and for light sets less than root n elements. Okay. So, what we can do in this problem is that after dividing the sets into heavy and light, we find the intersection of each heavy set with each light set. Okay. So as there are root n heavy sets and basically we can create a frequency array for every heavy set. Hmm. So we can create an array which shows if a particular element is present in a subset or not for heavy ones. So if these three are heavy for now, let's say, so f of f1 of 2 would be 1, f1 of 3 would be 1, and what else is there? 2, 3, 7, and 8. f1 of 7 would be 1, and so on. And for all those numbers which are not there, it would be 0. So it would be a Boolean array representing if a particular element is present in the heavy set or not. And we'll create this particular array, Boolean array, for each of the heavy sets. So overall the complexity would be, overall the space required would be f of, sorry, order of root n into max AI. AI max. AI max is okay, as AI max is order of 10 raised to 8 here, we can use the method of coordinate compression. And what happens is that we can ignore all those elements which are never going to come into the array. Uh, what I mean is that if there are n elements here at max at any time, and there are m updates, so overall only n plus m distinct elements can be here. N elements initially and m elements after the updates. Sorry, q elements after the updates. N plus q elements can be there. So we can do coordinate compression and we can remove the elements which are never going to come by some other element which is less than this n plus q. Okay. So let's say the only elements which we are encountering are 5, 100, 26, 1, 2, 3, 4, 5, 6, 7, and 6. These are the only elements which we are encountering. So we can simply replace them by 1, 2, 3, 4, 5 in an increasing order. Or we can simply replace them by 1, 2, 3, 4, 5 if you want to. Because the elements are of no use for us. Just the sum is of use to us. So we can, uh, so for one we can map it to 5. We can map 2 to 100. We can map 3 to 106. We can map 4 to this particular number. And we can map 5 to 6. So we can use 1, 2, 3, 4, 5 for frequency or Boolean arrays, and we can map them to their original values by calculating the sum. Okay, so for now let's consider that this particular number, is n as well, because we have already done coordinate compression. So after doing coordinate compression, we can assume these numbers to be 1, 2, 3, 4, 5, and in the frequency array. And yeah, now whenever we come across an update, so for light set, we can iterate to the element of the light set, and we can set AI for every I in Li. Let's say Li is the light set which we have to for which we have to update now. So for every I in Li, I will become I plus X. This operation. Okay. And sorry, AI will become AI plus X. L. L. So AI will become AI plus X, and we if we have to do the same update on a heavy set, we will just store that for this particular set X has been incremented. So we have another array H of U10, which is the maximum number of heavy sets. So initially they all will be 0, and whenever we are to update for any heavy set, we will make Hi plus equal to X if we have to update for the ith heavy set. Okay. So now comes the query answering part, and let's say we are given a set Si to answer query from, which means we have to add all the elements which are there in Si. So we have done all the light updates, or we have done all the light update with all the updates from the light set already there. The updates from the light set are already there, and we just have to incorporate the updates from the heavy set. So for light set, okay. So these are the elements which are in the set Si, and light updates are already there. So if we add these elements, or if we take the sum Si, we already have the sum of Si with light updates incorporated. And for heavy updates, we can iterate through the list of heavy. For the heavy updates, we can iterate through the list of heavy nodes for each Hi in I, for each Hj in. We can find the intersection of Si and Hj. So let's say I inter Si Hj is there. So we'll calculate the inter Si Hj, which we have already computed here. we'll find the intersection for every uh, SI and HI, light set and heavy set, by maintaining this particular frequency array. Yeah. So after computing the intersection of every SI and HI, we can uh, for every HJ in H, for every heavy set, we can calculate the number of elements which are common and the sums which have been done, and we can just uh, make this update that answer which was initially sum I plus summation of inter SI HI HJ times update which has been made on this particular update. So update on HJ. J is from 1 to root n. Okay. So this way we can compute the answer of our queries. This already incorporates the updates on light set and updates on heavy sets are handled by this one. Good. Okay, so we'll move to the complexity analysis part. So computing first the intersection, it is order of root n into n or ai max. Intersection of computing again and order of. Okay, for updates, we have to go through each of the heavy set. So it will become order of root n into q. And for updates, we have to go through the elements. Okay, update part is not the major part. It would also be order of q into root n because the number of elements in the light set is root n at max, less than root n. So it would again be order of q root n, q for queries and root n for elements in the light set. This q is for queries and the number of heavy sets. So overall, order of q plus AMX into root n. AMX is order of 1 8 over here in this question, but we can do coordinate compression and reduce these values to n plus 2. So n are equivalent to, we have just taken the maximum possible value of n to be n max equal to n. So this is how we categorize the elements into light sets and heavy sets, and we adopt different approaches for them. moving to the last part, last technique which I mentioned, which is the problems on entities having a fixed maximum sum, hence the limited number of distinct values. So what do we mean by this? Let's say you have been given a set of strings. So S1 is a string, S2 is a string, S3 is a string. The characters or the elements of the string are S11, S12, S13, S1, S21, S31. So if it has been said that summation of Si, the sizes of the string, is n, then the number of distinct sizes which can be there is order of root n. So how do we get through that particular observation? So let's say you are considering as many distinct values as possible. So you first consider one, the string is there of length one, then you consider the string of length two. So one plus two plus n max or minus max, which can be there, and the sum is coming out to be root n. Okay. So the number of distinct elements which can be there is, or if we compute the sum, it would be s max into s max this one by 2, and this is equal to n. Then maximum number of distinct values which can be there is order of 2n, and it is less than equal to 2n. It is of the roughly of the order of 2n. Okay? Root of 2n. Because these two can be considered equal, and we can take the root. We can also place less than 2. So this particular observation comes into use in several problems. I'll show you one of them. Okay, so this is a problem from Wutzer. In this problem, you have been given a tree with n nodes rooted at node 1. So the tree is there. And this is n nodes. Then R1 is 6 again. Let's consider n to be 6. And your task is to color each node of the tree either white or black. Okay, initially the tree is uncolored and you have to color it either white or black. Now for each I from 1 to n, let Wi be the number of white nodes that occurs in a simple path from the root node to the ith node. So let's say we color them black, white, white. So this is black maybe. This is white. This is black. This is white. So for the fourth node, B4 equal to 2 and W4 equal to 1. How is this? As we go from the root node to the fourth node, we come across two black nodes. Hence, P4 is 2 and we come across only one white node, hence W4 is 1. So these are the notations. WI is the number of white nodes in simple path from root node to ith node, and BI is the number of black nodes in simple path from root node to ith node. And the cost of a node I is defined as the absolute difference between Wi and Bi. So for the fourth node, the cost would be W4 minus V4, the absolute difference, which will be 1 in this case. Okay. Now, the cost of the tree is defined as the summation of the cost of all the nodes in the tree. So, cost of the tree equal to summation of cost I equal to summation of Wi minus Bi, the absolute difference. Okay. And Wi and Bi are the number of white nodes and black nodes from the root node to the ith node respectively. So okay, we also have value here. So the value of the tree is defined as the absolute difference between the total number of white nodes and the total number of black nodes in the tree. If the total number of white nodes is W white and B is the number of black nodes here, so the total number of the value of the tree would become B minus B. That's the difference. Okay. So these are the two values which we are asked to compute. And now we have to color the tree in such a way that the cost of the tree is minimized. Okay. In addition to that, we have to answer a single query Q, and if the Q is 1, we have to determine the maximum value the tree can have after minimizing the cost of the tree. Our primary objective is to minimize the cost of the tree. After that, we have to determine the maximum value which is possible for the tree. And the second query asks us to find the minimum value after minimizing the cost of the tree. So in both the queries, we have to minimize the cost of the tree first, and then we have to determine the maximum value or the minimum value which the tree can have. Okay. For this particular part, where you have to compute the maximum value the tree can have, we don't need square root techniques or anything. You can also look at the points. So if you solve only the first part of the problem, you get 20 points, and square root techniques should not be used for 20 points. So we'll use square root technique if you want to have all 100 points. So how can we do that? So let's consider this tree only. For this node, if we want to minimize the cost will be 1 irrespective of the color of this node. So if I change it from B to W, the cost will remain 1 because there is only one node, and it can either have black or white, not both. So the difference between B1 and W1 would be 1 only. For this node, if we have the first node set to 1 or set to W, we can change this to black, and then the cost for this node would become 0. W2 minus B2 becomes 0 because we have one black node while moving from the root node to the second node, and we have one white node while moving to the root node to the second node. So in both the cases, this particular value is 0 only. Hence, there is a way to minimize the value, minimize the cost for this particular node. Coming to this node, as you can see, this is black already here, and for black, we have the cost to be W1 minus, sorry, W3 minus V3, which is 1 minus 1. Hence, the cost here is 0 as well. If we come to this node or this node, we can see that we can never make the value of the cost 0. As there are odd number of nodes, the difference would at least be 1. So we'll try to make that 1 only. So as you can see, if we make it W, then the cost is 1. If we make it black, then the cost is 1 in that case as well. So for nodes of odd level, the cost is 1. And for the nodes of even level, the cost is 0. Saying this, let's say if we can minimize the cost of node 6 to be 0. So if the color of 6 is black, the cost will become W6 minus V6, which is 0 only. And if the color is white, then W6 minus V6 will be 2. So why to make it 2 when you can have it as 0? Because you need to minimize the cost. Hence they make it black only, because it minimizes the cost of the whole tree. So we have come to this particular conclusion that for every node at, this is the odd value, even level, these are the nodes at even odd level, and this is the node at both level, this is even. So for every nodes, for every single node of an even level, we can have the cost to be 0, and for every single node of the odd level, the cost is coming out to be 1. So overall, the cost minimum of the whole tree will be equal to number of nodes in odd levels. So after minimizing the cost, what we have to do, we have to minimize the value of the tree as well. So in the second query, you have to determine the minimum value that tree can have after minimizing the cost of the tree. So we have already done the cost minimizing part. Now we have to minimize the value. So how can you do that? What is the value of the tree in this case? Yeah. In this particular case, we have 1, 2, and yeah, just 1, 2, 2 white nodes. And we have 1, 2, 3, 4, 4 black nodes. So the value is 4 minus 2, which is equal to 2. Okay. And the cost is 1, 2, 3. 3 nodes at odd level, so the cost is 3. Okay. So cost is 3 and value is 2. Now, if I change this black to white, will my cost be affected? The number of nodes at odd levels is not changing. The number of nodes is always constant. So we can change the values of the odd levels, and we won't find any change in the minimum cost which we have acquired. It's just that if we change the value here, let's say if I am making it black, then I'll have to change the color of my children as well, children of the node as well. After doing this change, the cost is again minimized. And let's consider this example. If I'm making this black, then I'll have to change the color of its children to white. And again, the cost is same, minimum. You can see. If I change it from white to black, the cost will still remain the same. So we can make collections. We can make collections of nodes at odd levels along with their children. So this is one collection, this is another one, this is another one. If we had another node here, then this would become another collection along with its children. Okay, so a particular collection comprises of a node at an odd level along with its children. So if we are changing the color of the node or the parent of the collection, we will have to change the color of the children as well to the opposite of the color of the parent. If this is colored black white, then these all will be colored black, and if this will colored black, then all this will be colored white. Okay, so how will we decide if we have to make the color of the parent to be black or white? This is where the minimum value comes into picture. So let's consider one collection as of now. Collection of node at an odd level along with its children. This is colored black, and all these are colored white from them. This is this particular collection only. So how much does this contribute to the value? Okay, there are three white nodes over here and one black node over here. So let's say in our tree, the number of white nodes is always greater than or equal to the number of black nodes. So the contribution from this particular collection would be 2 or 3W minus 1 black equal to 2. So and so we have the contribution from this particular set. If the set had no children, let's say this particular node at odd level had no children, you can consider 5 for example, as this has no children. So if we color it W, its contribution would be 1. And if we color it black, its contribution would be -1. Okay, but as we are considering the white to be greater than or equal to black, we will preferably color it white only. Okay, so we can consider all these collections separately, and we can calculate the contribution which is being made by all these collections separately. The contribution of this collection is plus or minus 3. The contribution of this collection is plus or minus 1. The contribution of this collection is 0, as both of these are of opposite colors and hence no specific contribution. The contribution of this is 1. So contribution equals to number of children minus 1. This can be positive or negative. Okay. So we make an array or we make a vector and store all the contributions of all the collections. So let's say contribution array is there. Has values 5, In this particular case of ours, it has values 2. Okay, this is 3 minus 1, so it is 2. So 2, 0, 1, and 1. So 2, 0, 1, and 1 are here. So we'll make some of them positive and some of them negative. Okay. And by doing this, we have to minimize the cost of the, sorry, we have to minimize the value of the complete tree. Okay. What does this value indicate? Number of children minus number of parent. Number of parent is 1 obviously. So we'll color all the children in the same color and the parent in the opposite color. So this becomes 2 and so on in all the directions. Now we have been given an array of these collections, contribution from the collections. And as these are the number of nodes only, the number of children nodes minus 1, the sum of all quantile contributions will never exceed n, which is the number of nodes. As the total number of nodes are n, and we are only considering the nodes of even level minus 1, the maximum value would never surpass n. Okay, so what does this tell us? This tells us that the number of distinct values which are there in this particular vector, distinct values, would be less than or equal to root of 2n because of the property which I showed you earlier. Yeah, this is the property. If m numbers are there, then sorry, if the number of some elements, if the sum of some elements is less than or equal to n, then the number of distinct elements between those elements would be less than 2, less than 2 root 2. Okay, so we've seen that the distinct elements are root of 2 and only here. Wait for a moment. Yeah, so coming back, distinct values are root of 2 and only. So we can create a frequency array or a map where we can store the frequency of each of the element. So in this case, it would become frequency of 1 will be 2, frequency of 2 would be 1, and frequency of 0 would be 1. Okay, and we can have some of these as positive and some of these as negative. So what we are basically doing here is that we are finding or we are computing an abstract DP problem to compute the minimum positive score which is possible, taking some of these numbers as positive and some of these numbers as negative. Or this can also be written as if the sum uh, is the sum of if the sum of the first category or the positive category is sum and the total sum is summation of Si, then we have to find the absolute difference between sum minus the remaining bit, which will be absolute difference between absolute value of Si minus 2 times of sum. Okay, so this is the value we are looking for. Minimum value possible. because we have to minimize the cost. Okay. So what are the possible summations here? As this value is constant, we want this value to be as less as possible, right? So what is the minimum possible value, or what is the value which is closest to Si by 2 in order to have this value as minimum, or this difference as minimum? So we'll make an website and we'll calculate what values are possible, and we will take the value which is closest to Si by 2, so that this value will be closest to 0 and we'll get the minimum value. But computing an AppSec, okay, let's try computing an AppSec. So if there are n elements over here, as said, n elements, you can compute an knapsack in order of n square. It is a standard DP algorithm. But as you can see in the problem, the value of n is given to be 25. Hence, we cannot compute a direct knapsack here. What we are doing is that we are considering the distinct values one by one, and we are taking their contributions individually. So let me show you the code itself. This is my submission for this problem. Yeah. So here I have computed I have declared a Boolean vector which shows if a value is there or not. And there is a map. Let me show you. Yeah. This particular map is the frequency array which I was talking about. If it has it's what is the frequency of the distinct value which it has, which the vector has. Okay. And possible Boolean vector shows us if a particular sum is possible or not. So we'll iterate through the elements of map, or the frequency array in this case, this particular frequency array. And for every element of in the map, what we'll do, we'll iterate our possible array from the maximum value, which is summation of Si in our case, and till 0. And if some value is possible already, then we'll take all the possible number of occurrences the particular value can take, which was 0, which was 1 for 0, 2 for 1, and 1 for 2. 1 can be taken 2 times. So if we are iterating over 1, then we can take it for a maximum of 2 times, which is it.second here. So while iterating through map, we'll check first if a particular x is possible, and if that particular x is possible, we'll run this particular loop from I equals to 1 to the maximum the I can take, which is the frequency, and we'll make the pause of that particular value to be 1 if that lies in the limit of the maximum value. So repeat transition would be for all I in frequency table for j from n to 1 if, so let's make it simple side, if possible summation of j, if possible j, then we'll take all the possible occurrences of frequency k from 1 to I will make pos of j plus frac I j plus k into I as 1. We can take k to be any number from 1 to frac I, frequency of I, and we'll make cos of j, which was already possible, plus k times I to be 1. In this case, in this way we can calculate all the possible sums which can be there. So cos of I will ultimately tell us if it is possible or if it is possible to make a sum of I out of these elements. So basically what knapsack does. So we are just optimizing the knapsack to be able to run a row of n to 10, where the overall sum is limited to n, sum of the distinct elements. So yeah, so the total number of distinct elements comes out to be n root n distinct and n total for summation values. So root n comes out from here and n comes from here. As you can see, root n comes from this particular line, as only root n distinct elements are there, root n or root 2n, and n comes from here, as the maximum number of elements can be n. So this way, this problem can also be solved in order of n root n. So these were the 5 major techniques which are heuristic techniques which are used in competitive programming. And yeah, these problems you can take for reference. I'll put them in chat. You can try solving other problems as well. You can try using solving this particular first problem using the third technique, which is the batch processing technique. Yeah, so if you have any doubts, you can ask in the comment section, chat section. Thanks to all for attending the session. The lecture recording would be there if you want to rewatch or anything. And I'll post this particular document consisting of the links to the problems. And thank you for attending.